Hi guys, good evening everyone. Yes, good afternoon guys. Sorry, this time we are meeting on good afternoon, not an evening. So sometimes this happens, like when you have usually on a time, so you remember that only. So yeah, good afternoon everyone. I hope everyone is doing well. So I'm so sorry the class got little like started late. There was little issue with this uh, like the stream key, so that's why it took little time. No problem. Let's just quickly start with the yes, let's just quickly start with the topic. Okay. So what we'll be discussing is, guys, yes, we'll be discussing about today the topic, which is nothing but yes, crystal field theory. So let's just start with it, guys. So sorry. We have to start with the crystal field theory today. So let's just start with it. Yeah, very good. So, okay, what is crystal field theory? We'll be discussing. It's a very important topic of coordination compounds. But yeah, before starting with it, all those learners who are new on our platform, for them, quickly let me just introduce myself. So, guys, I'm Manisha Rani, your chemistry educator at Unacademy. I have experience of online and offline teaching at reputed institutes for more than 5 years. I have completed my master's from NIT Warangal and bachelor's from Delhi University. I have cracked IIT JAM, CSIR NET, and GATE, and I have given best ranks through my students, and I'm a plus verified tutor, guys. So this is about me. All those who new learners who are coming on the platform, so I want them also to introduce their self so that I'll be knowing about them. Okay, so let's just start without wasting time. Let's just start with what is yes crystal field theory and how it can help us to understand about coordination compounds, because it's a topic of, guys, coordination compounds. It's a topic of coordination compounds. So what we can relate? Yeah, the crystal field theory came after VBT. So obviously VBT was having some limitation. Now, talking about crystal field theory, what it helped us and what it said different than the valence bond theory, that's what we have to understand. So basically, valence bond theory considered the bond between yes metal and ligand as covalent only, because it considered as like specifically coordinate bond, right? But what you can relate, all of you must be knowing that coordinate bond is nothing but it's a type of covalent bond only, right? Now we have to understand what crystal field theory said. So crystal field theory considered the electrostatic model. Okay, what it considered? It considered that the bond is not only covalent but it has a ionic character as well. Okay, so it considered even the ionic character of bond, and that's what we have to know. Now talking about, okay, all those postulates we can understand, but what is the main thing that it said? It said that when we have a d orbital, until and unless a ligand doesn't approach it, it is degenerate, right? All of you must be knowing that d orbital here, which and all are there in this, the d subshell dxy, dyz, dxz, dx square minus y square, and dz square, right? They all are considered to be degenerate. Why? What is the meaning of degenerate? Can anyone tell? Degenerate means nothing but yes, they all have same energy. But what happens? No, yes, whenever a ligand approaches any metal atom, right, what happens? This d orbital quickly splits up into two energy levels. What happens? This d orbital quickly degenerates in, like, quickly breaks into two set of energy orbitals. But how this happens? Whenever a ligand approaches d orbital, first its energy is going to increase. This is a correct way to represent. Many of the students, they just show the splitting. Remember, guys, when a ligand approaches, okay, when a ligand approaches a metal, what happens? Your d orbital energy increases and then it splits up into two set of energy orbitals. So depending upon what ligands are coming, so if a octahedral field is there, depending upon how many ligands are approaching. Like suppose if you have a metal, to that 6 ligands are approaching and forming Ml6 type of complex. Like it is providing octahedral field. 6 ligands they have approached, right? So what happens? Your d orbital actually breaks down into two set of orbital. One is considered as T2G and another is considered as EG. One is considered as T2G and another is considered as EG. Okay, now T2G is triply degenerate, while EG is doubly degenerate. It is doubly degenerate. Okay guys, very good. Now the difference of energy which is there in between T2G and EG is called as, yes, it is represented as dello. Yes, it is represented as dello, which is nothing but crystal field splitting energy. Yes, this dello is nothing but, yeah, it means crystal field splitting energy. So basically I was giving you an idea about crystal field theory. So in crystal field theory, right, what is there is, it's simple. Whenever a ligand approaches metal degeneracy, metals d orbital, because we are going to talk about coordination compounds, and in coordination compounds we talk about transition metals. In transition metals, d orbital is there, and then in that d orbital obviously it has a degeneracy. What do you mean by degeneracy? All the orbitals, they have a same energy, like dxy, dyz, dxz, dz square, dx square minus y square, they all have the same energy. But what happens, the moment ligands approach metal atom, the degeneracy of the d orbital breaks. How? After increasing its energy. Because what happened, no, the moment any ligand are going to approach a metal atom, what is going to happen? It's going to get excited, and it's going to get excited, so obviously its energy is going to increase. Once energy increases, what is going to happen? It's going to split up into two set of orbitals. One is considered as T2G and another is considered as EG. T2G is triply degenerate, while EG is doubly degenerate, right? Means you have two orbitals here, and in T2G you have three orbitals. So basically if I talk about in T2G, we have dxy, dyz and dxz, and EG we have dx square minus y square and dz square, like that, axial and non-axial d orbitals. I hope everyone is clear. So this is what it happens in octahedral field. So I'll be quickly telling about it again, because we have to understand about this diagram little more. So we understood we have a d orbital which is degenerate, correct? It's degenerate, correct? But what we have to understand here, yes, a simple thing, that when 6 ligands means in the octahedral field, good afternoon Abhishek, in the octahedral field, what happened means when 6 ligands approach, first the d orbital energy increases, correct? The d orbital energy is going to increase, and after that what happens, guys? Yes, it splits up into two set of orbital. One is considered as T2G and another is considered as EG. EG has more energy than the excited one, and T2G has less energy than the excited one. Now I told you that in between the energy difference is considered as what, guys? It is considered dello. The energy difference between EG and T2G is considered as dello, which is nothing but crystal field splitting energy for octahedral field. This is crystal field splitting energy for octahedral field. For octahedral field, correct? Very good. Now what you can relate, we can say that this crystal field splitting energy, how it is divided. So if you will see that from this level, which was the excited energy level, which is called as barycenter. This is called as, guys, barycenter, because from here only it is increasing or decreasing, no? So what is found is that here the energy of Eg is around 3 by 5. It's more, no? 3 by 5 of dello, right? And it's positive. Positive is telling that it is more, it is increasing, while here the T2G and barycenter difference is minus 2 by 5 dello. Okay, so from barycenter to Eg, the difference is 3 by 5 dello. Okay, here the difference is plus 3 by 5 dello of, means dello means 3 by 5 of crystal field splitting energy, and here it is decreasing from barycenter for T2G. The energy is less. How much? Minus 2 by 5 of del O. Very good. Okay, so if we understood this values, right, we can relate with many of the things. But yeah, now once you have understood about that crystal field splitting occurs, so when any of the complex is given, guys, yes, you will be filling the electrons in T2G and EG orbitals. Like, let's just understand, and it is going to be influenced by how it is going to be filled. T2G and EG, it's going to be influenced by the strength of the ligand, whether it's strong ligand, weak ligand. So it is going to be dependent on that. But before that, let me tell you that we discuss mainly two types of complex. One is in the octahedral field, another is in the tetrahedral field. So let's just discuss what is going to happen when a ligand is going to approach, but it is 4 ligands. So it is forming a ML4 type of complex. So we can relate crystal field splitting in tetrahedral field. Crystal field splitting in tetrahedral field. Okay, crystal field splitting in tetrahedral field. So how it is going to happen? It's very simple. Tetrahedral field means 4 ligands are going to approach. So again, your d orbital will be degenerate. Okay, once 4 ligands will approach this d orbital, means tetrahedral field, what is going to happen? The d orbital energy increases, yes or no? The d orbital energy is going to increase. It's going to get excited, and after that it's going to break. Yes, it is going to break in T2G and EG. But here what you have to relate, guys, that T2G will be lying above and EG will be lying down. It's going to be opposite. So in tetrahedral and octahedral field, the splitting is, guys, opposite. Yes, this is what you all have to know, that splitting is opposite. What we can understand here, that when 4 ligands approach, same way energy gets excited, like the d orbital gets excited and its energy increases. But what happens, here the splitting will be what? You will be getting EG and T2G. EG will be having a lesser energy and T2G will be having more energy than barycenter. So this is my barycenter, because from here the energy is increasing or decreasing. I can relate that. This is barycenter. Now how much more, like T2G, how much value it will be increasing? So it's fixed, like what was there for the T2G, but here it will increase. 2 by 5 del O increases, while here minus 3 by 5 del, not O, it will be del T, because it's a crystal field splitting energy for tetrahedral field, and for that we denote it with del T. We can mention del T here and even here del T. So what is del T first of all? Yes, del T is crystal field splitting energy in tetrahedral field. Okay, and what you can relate, for the T2G energy is increasing while EG energy is decreasing. Very good. So here we have understood that the splitting takes place differently in octahedral and tetrahedral field. It's not going to be same, it's just opposite. What happens in octahedral field? If you remember that, you can easily write what is going to happen in the tetrahedral field as well, because in tetrahedral field it's just opposite. Here you will have down eg, and then t to g you are going to have above. Okay, what was the value from berry center to t to g? It is this only, 2 by 5 only, but now because it's above, so it will be positive, so it is increasing. Okay, for eg it was 3 by 5, here also 3 by 5, but in tetrahedral field, because it is down, so it will be decreasing. So you can relate with it very easily. I hope everyone is clear till here. Anyone is having any doubt, tell me guys. Yes, Abhishek, everyone. Now talking about the next thing, which is spectrochemical series, because that is going to help us to understand how the filling of electrons will take place in T2G and EG. So we have to know about spectrochemical series. Spectrochemical series helps us to find out the strength of the ligand. Strength of the ligand as in that spectrochemical series is a arrangement of ligands in order of their strength. So what you have to know, accordingly we can find it out that which one are weak ligands, which one are strong ligands. So iodine is the weakest one, then you have bromide, thiocyanide, chloride, sulfide. So this is the order which we all have to know. What is the order? Yeah, yes, I hope everyone knows it. Iodide, bromide, thiocyanide, chloride, sulfide, fluoride, hydroxide, oxalate, then you have water, then you have isothiocyanate. Yes, NSC, NCS. Okay, NCS minus, then EDTA4 minus, ethylene diamine tetraacetate. Then what else you have is ammonia, ethylene diamine, cyanide, and yes, you can learn with the trick this. Okay, so what you can relate is Abhishek, that we can make any of the mnemonics related to it, right? So whatever language you are comfortable in, Abhishek, like suppose if you are comfortable in Hindi or say any language, so you can remember any names from this names, right? So I can give you my mnemonic also, but I think that won't help you that much the way if you will make your mnemonic. Like suppose, because you remember those names easily, you know, like suppose from I you remember some name, right, which you can like say anything, you can say ice cream, right, or you can say any terms, like getting this point guys, like for I B S you can make any what, any of the names you can give it to it, and then learn. By that you will be easily able to remember. So this is how you can remember the spectrochemical series. There are many mnemonics as well which are there, but I will suggest that you should follow, you should make always your own mnemonics, because by that way you won't do any mistake. You can learn other mnemonics as well, right? Like if I give you very common Isha, yes, okay, so you know Isha, right? So Isha, then you have a B, from B you know any name, Bablu, है ना, Sharad, any name you can remember, right? Charles, all of them are my friends, right? Are Shirish friends, like that you can remember, you can make any. Getting this point? Yes, so by that you will remember it so easily and you will never forget it. So this is how you can remember it. Now if I tell how we can relate with the order, so the order is, in the starting whatever ligands we have, they are considered as weak field ligands. What they are considered guys? They are considered as weak field ligands till water. They are weak field ligands. Okay, till water they are weak field ligands, and after that you can consider them, they are strong field ligands. Strong field ligands. So how you arranged them, how you considered one as strong field and another as weak field. So it is an experimentally determined series, guys, right? Experimentally we have find it out their field strength, and that actually depends upon their crystal field splitting also. Okay, the ligand which is able to cause more crystal field splitting is a stronger ligand, the one which is not is a weak field ligand. Like that, they did experimental studies of all the ligands, and they got to know which one all are strong and weak ligands. So talking about it, what is the important thing which we have to learn here? So remember that, guys. Yes, the weak field ligands, WFL, we can write weak field ligands is WFL in short form, while strong field ligand we can write in short form SFL. Okay, so the WFL means strong, which one? The weak field ligands do not cause pairing of electrons, while SFL, strong field ligand, causes pairing of electrons while filling T2G and EG in configuration, while filling T2G and EG. Like for example, let's just take one examples for this. Like suppose you have CONH3 6 positive, like CONH3 6 3 positive. This is the complex. Okay, so if I talk about cobalt here, it is in what oxidation state? It is having 3 plus charge over here, because ammonia is neutral ligand. So what is the d orbital configuration here? Tell me. D orbital configuration is, yes, argon 4s2. So iron cobalt 27 it is, but you have removed 3 electron. So like suppose if I talk about here, first you can write cobalt only configuration so that you won't get confused. Cobalt is 27 atomic number. So 27 it will be 4s2 3d7. But you're removing 3 electrons. There is a 3 plus charge. So you will remove first 2 electrons from 4s and 1 electron from d. So what will happen in CO3 plus? You will get argon 4s0 3d6. So basically you have 3d6 configuration, correct? So 3d6 means it is like this: 1 2 3 4 5 6, correct? So when ammonia, there are 6 ligands, right? So it's octahedral field or tetrahedral field? Tell me. 6 ligands, no? So it is octahedral field, correct? Abhishek, everyone? Very good. So what will happen? Its energy first will increase and then will break in the T2G and EG. So you will have down T2G and above you have EG. So actually how you will be filling? Yes. So ammonia is a strong ligand or weak ligand? Tell me. Everyone in the chat. Ammonia is a strong ligand or weak ligand? Yeah. It's a strong ligand. Ammonia is a strong ligand. So what will happen? No. Because it's a strong ligand, what you can relate is, it is going to fill first T2G completely, 1 2 3 4 5 6, and then it will go to EG. Because it's a strong field ligand, it will cause the pairing of electron. So T2G first it will fill and then EG will go. So this is how then the electron is going to go in the EG. Okay, but suppose if you have the same type of complex, you have COF6 3 minus. Okay, like suppose if you have another complex, what it is? You have COF6 3 minus. COF6 3 minus. So in this COF6 3 minus, you can relate that cobalt oxidation state. I can find it out. What it will be? X plus minus 1 into 6 is equal to minus 3. So X is minus 3 plus 6 is 3. So cobalt is in plus 3 only. So first I will write the configuration: argon 4s2 3d. Yes, 4s2 3d what? 3d7. Again CU in plus 3 oxidation state. So it will be argon 4s0 3d6. 6 ligands only are there. So D will get filled like this, but when, because 6 ligands are approaching it, so first its energy will increase and then it will undergo splitting. So it will undergo splitting in this only, Eg and T2G. Correct. But yeah, it is octahedral field. Now what you can relate is, it's simple, that because it's fluorine is a weak ligand. If you will see here guys, fluorine is a weak ligand. So what you can relate guys, yes, what you can relate is simple, fluorine is a weak ligand. So fluorine is a weak ligand, so it won't undergo pairing. So first you will fill everything half, 1, 2, 3, 4, 5, and then you will make it fully filled. Getting this point guys, yes or no? Yes. So on the basis of this, we can answer many of the questions, right? On the basis of this, we can answer many of the questions. Okay. So basically, first, if I say, what we have understood, that crystal field theory said that one thing, that the bond is not completely covalent, it has ionic character as well. Then the second thing what it said, whenever the ligand approaches a metal atom, its d orbital energy increases, and then it gets splitted up into two set of energy orbitals. One is considered as T2G, which is triply degenerate, another is EG. If it's an octahedral field, it is going to break, yes, in such a manner that T2G will be down, having lesser energy than the excited one, and EG will be above. While if it will be there in a tetrahedral field, what is going to happen guys? Yes, it will be just opposite. EG will be having lesser energy than the excited one, and T2G will be having more energy than the excited one. Okay, like same way, if I'm giving you a complex for the tetrahedral field, which will be easily able to relate. So say you have a tetrahedral field complex NiCN4 2 minus. So what you will do, first you will find it out what is the charge on nickel. Yes, so nickel, first you will write normal configuration. Its atomic number is 28. So it will be argon 4s2 3d8. Correct. But here what is the charge on nickel? X plus minus 1 into 4 is equal to minus 2. So x is equal to minus 2 plus 4, which is plus 2. So nickel is having plus 2 charge. So I will remove 2 electrons from here. So it will be 4s0 and 3d8. Okay, now what will happen? Cyanide is a strong ligand or weak ligand guys? Tell me. 5, 6, 8. It's a strong ligand, correct? So what is going to happen? First its energy is going to increase, and once its energy is going to increase, what will happen? It will get splitted into set of 2 energy orbitals, correct? So your 3d8, right? First the energy increases the moment 4 cyanide ligands will approach, and what will happen? But it is going to break as Eg and T2G. Eg will be down and T2G will be above. Correct. Now cyanide is a strong ligand, so how you will fill that? 1, 2, 3, 4. First you will complete, you will make it filled the Eg orbital, and then you will go and fill remaining 5, 6, 7, 8. Like that you will be having. Clear with it or not? Because it's a strong ligand, first you will make the down degenerate orbital only filled, and then you will go above. But suppose if you are having same way, NiCl4 2 minus, yes, NiCl4 2 minus. So what is going to happen guys? Yes, NiCl4 2 minus. So what is going to happen is a simple thing. Yes, you will have nickel again. You will write argon 4s2 3d8. But here also nickel is in plus 2 charge. You can find it out same way. It will be argon 3d8. Right? Your d orbital will be degenerate first, but 4 ligands tetrahedral field, when they are going to apply, its energy is going to increase, right? And once its energy increases, it's going to split up into 2 set of orbital. One will be Eg, another will be T2G. But because the chlorine is a weak field ligand guys, what is going to happen? Yes, first you will make everything half filled, and then only you will start making it fully filled. So Eg How much you have? Like 6. You have T2G 3, no? Sorry. So T2G you have 3 and EG you have 2, right? See, we can make it again once. So you have T2G above and EG down. So first you will make everything half filled because it's a weak ligand. 1, 2, 3, 4, 5, 6, 7, 8. So this will be the configuration if you have a weak filled ligand. Very good. Correct, Abhishek. It's sp3 hybridization. I hope everyone is able to relate. Yeah. So with this, we can actually relate many of the other parameters too. Okay. But what we have discussed in today's session, we have discussed about the crystal field splitting, crystal field theory, in that we have understood about crystal field splitting in octahedral and tetrahedral field, and how the filling of electrons are going to get affected with the strong field and weak field ligand. From here we have understood very well that in octahedral field and tetrahedral field the splitting is absolutely opposite. Okay, and strong field ligand will be able to do the pairing of electrons. Weak field ligand cannot do the pairing of electrons. Strong field ligand, first whatever orbital is getting filled, it will make sure that first it is getting filled and then the electrons are going to the next one. But weak field ligand first will make everything to be half filled and then only it will start doing the pairing. Clear with it, everyone? Yes. So this is what we have discussed today in crystal field splitting. In a short span of time, in half an hour, we have discussed about both the things, that how in octahedral field and tetrahedral field crystal field splitting take place. I hope all of you understood. So make sure you are revising this topic, and if you get any doubt, do let me know in the next session. So guys, this way only we have some classes, right, going on for 1 hour in the Unacademy platform, and there we will be discussing all those topics which you face difficulty in. So if you want to discuss any topic, you want me to teach any specific topic, you can let me know in the comment section, and I will be creating either a special class on Unacademy platform or on YouTube. Will be having one class related to that topic so that you can get it clarified, all your doubts. Okay, so yeah. Okay guys, then we'll be meeting in the next session. Thank you all of you. Bye bye. Make sure you are pressing the bell icon so that you will be getting all the information regarding my classes. So okay guys, thank you everyone. Bye bye. Bye Abhishek. Bye everyone. Okay, thank you Abhishek. Thank you everyone. Bye.